Today we are going to talk about the type of energy that is transferred in the form of waves. And different types of energy have different properties of the waves that they travel. If you look on this chart, we notice that there are some waves up here that are dangerous to us. For example, ultraviolet rays, X-rays, gamma rays if we're not protected properly. However, other waves like radio waves that we have going all throughout our entire Earth now are not dangerous to us. And so with different waves come different properties that they have, and collectively this makes up our electromagnetic spectrum. We have talked a little bit already about some of the different properties of waves, and you see some of those on the left-hand side. So for example, wavelength, frequency. Those are words that we have talked about before and also would give attributes to these certain types of waves. So now let's kind of talk about what makes a wave and how these different energies in the electromagnetic spectrum are used or created. First, let's take a look at the anatomy of waves. A crest is the highest point on a wave. The trough is the lowest point. The amplitude is the height, or also you could take the distance below from the mid to the crest or mid to the trough. And the wavelength is crest to crest or trough to trough. The only other word that is missing here is the frequency, which would be how often the wave occurs. And so things to remember when we talk about waves, and also as we now talk about the electromagnetic spectrum, the higher the frequency, the more energy the wave has, which makes sense. If you have a lot of waves that are being received, that means it has more energy. Electromagnetic waves do not require a media in which to travel. So it doesn't need to have air. It doesn't need to have gas. It doesn't need to have liquid. And we know this because we can feel the heat from the sun, even though there's no air in space. Electromagnetic waves are considered to be transverse waves. We'll look at that in just a little bit. And so the other thing, the fourth point here, there's an inverse relationship between wave size and frequency, which again makes good sense. If you have wavelengths that are smaller, usually the frequencies get higher. So now let's talk about some of these different types of electromagnetic waves. The first, radio waves. So hopefully you know now that radio waves are not dangerous to us. However, they are around us all the time. And these are waves that have really long wavelengths and low frequencies. So we talked in the previous presentations about how when we dial in our radio to, let's say, 98.3, 99.9, we are tuning in to a certain frequency. And so when we look at, radio waves, there's actually different kinds of them. The shortest one is the microwave, which we know is used for cooking, very good energy to them. And then we also have or use them with radar, cooking food obviously in our microwave. And then they also help us with satellite transmissions as well. So when we look at going back to the radio waves, they are over here. Okay, so we're seeing the radio waves, the AM ones, and then we are seeing the FM radio, and then the microwave. And remember, as we go here, we are getting a higher frequency, and so we really use the energy from that to cook our food. So collectively, they are referred to as the radio waves. Continuing, let's get into next are infrared rays, also known as heat. So they have a shorter wavelength, but a higher frequency. So you can use these to, for example, find people that are in the dark. We also use infrared waves, or we can see this with using heat goggles as well. Visible light is what we can actually see in the electromagnetic spectrum. So we can't see heat. We have to have an instrument that helps us with that. We can't see microwaves. Yeah, we can see the box or the appliance, but we can't see the actual waves within it. We can't see ultraviolet rays. So visible light is the wavelengths that we can actually see. So it's about 700 nanometers to 400 nanometers, and we'll talk about those in just a sec. And when we look at the wavelengths, the different wavelengths are different colors. So, very famous mnemonic to use for this is Roy G. Biv. Those of you that like Pink Floyd, a prism takes white light and is able to convert that into all the different lights that make up white light. We know this also when we wear white in the summer, we don't get as hot as when we wear black. Black absorbs all of the different colors, thus, it heats it up because it's absorbing more energy. White reflects all of those colors. So Roy G. Biv stands for red, orange, yellow, green, blue, indigo, violet. He is a very famous person, not a literal person, but that's how we remember these letters. They also go in the order of wavelength. So let's take, for example, plants. This is very real life. Most plants are what color? Green. Question 2. Do plants use green light to go through photosynthesis? No. The color that we see is actually being reflected back to our eye. So even though plants themselves are green, they do not use the green wavelength of light. What this means is if I had, let's say, a plant tray with different lights, and let's say I have red lights, and I had a green light, and I had a violet light, the green lighted plants would not grow very well at all because that's what color plants are. So it's kind of a unique way, and we'll talk about that a lot in biology. So continuing on, ultraviolet light. Remember, this is stuff that we can't see, but these have a very high frequency, and therefore they have a lot of energy. And these types of rays can penetrate through cells. Very, very important for us to talk about this with sunscreen, because sunscreen is actually able to reflect and get rid of ultraviolet rays. Our ozone in the atmosphere reflects UV rays, so these would not be good if they were to become more obvious in our Earth. And then the last one that we'll talk about are X-rays. So those of you that have gotten X-rays before, you might have had to wear like a lead blanket. And the reason for that is you want to protect the inside parts of your body, especially the reproductive structure. So oftentimes you wear them like around your waist to protect your reproductive structures. We use X-rays especially with seeing bone, because bone, as we know, is a very dense material, and it's also made out of ions such as calcium and phosphorus that allow the light of X-ray, not the actual light, but the waves of the X-ray to be reflected back and actually get an image. Where if we look at like the tissues, here'd be like our gums, that doesn't reflect because it's made out of a soft body tissue. So let's now talk about these waves a little bit further, waves and waves properties. So there's two different kinds of waves, and these would be important for us to know. First of all, if a wave does travel through a medium, it's what we call a mechanical wave. So this would be something like sound. If you put a speaker really loud in front of a cup, you would be able to see it vibrate from the sound or from the vibration on the table that the cup is sitting on. If waves can travel without a medium, then it's called the electromagnetic wave, or EM, or the electromagnetic spectrum. So let's talk about these two different kinds of waves that we have. The first type is what we call transverse wave. And this is something that is going to move what we would consider like up and down in the direction of the wave. So waves in the medium moves at the right angles to the direction of the wave. Compression waves, however, they are going to be more of just that, compression. Think of this as like an accordion or a slinky or a spring, where they're actually just going to kind of be vibrating back and forth. There's going to be moments of compression, but then also moments of extension. So transverse waves, think of them for our sake as up and down. And then compression waves, think of them as basically being back and forth types of waves. So waves, as we said, there's language to them. Crest and trough, amplitude, wavelength, and then frequency is arguably one of the most important factors, especially with the electromagnetic spectrum. And when we look at this, so this would be, for example, our transverse wave, because we're saying that it's going up and down, where a compression wave, we are looking for how those molecules are moving within that area. And we can see this with what we call a tuning fork and the sound that is given off with them. So, our topic for today was talking about, first of all, the anatomy of waves. So, this is certainly language that is good for us to know. And then also the electromagnetic spectrum, and just understanding that we have this whole group of energy called the electromagnetic type of energy that travels in waves. And so, again, our examples that we talked about would be radio waves, microwaves, infrared, which is also known as heat. We have the tiny, tiny little bit of waves that we can see. It's known as visible light, and we see a bunch of different colors. All those colors means is that they have their own wavelength. That's it. People that are colorblind, that just means that they can't see certain wavelengths of lights with their cones that they have in the back of their retina of the eye. Ultraviolet, soft X-rays, hard X-rays, and then gamma rays. So as we get, especially after visible light, we really start to see some of those dangerous waves that we want to protect ourselves from. So that concludes our presentation on electromagnetic spectrum and also the anatomy of waves. Hope you've enjoyed, and thanks for tuning in.